Welcome back. We are on segment number 3 and we're looking at work, energy and power. Okay. Work is the product of force and displacement, where the force is in the same direction as the displacement. And we're going to explain further what we mean by this. Okay. Now, this would mean that this work we're talking about should be equal to force times the distance. And because we're saying that this force must be in the direction of the displacement, then we say cos theta. That is bringing the force component that is in the direction of the displacement. Therefore, that is the force that is doing the work all the time. So sometimes we're going to have forces acting at angles. Okay, we should be able to work out what that component is that is doing the work. Hence, the cos theta thing there. Work is measured in joules. These are the unit of the SI units of measurement for work. And you can see immediately that work is therefore related to energy. Of course, energy is the ability to do work. All right. Now, energy is the ability to do work, as I have just said. When a force is applied at an angle and work is done on the object, the component of the force parallel to the displacement, in other words, in the same direction as the work that is done, sometimes not necessarily in the same direction, but parallel, which means acting either in the direction of motion or opposite the direction of motion. That force is the one that is responsible for the work done. So in this case, we can even find resultant forces for forces that are acting on the same horizontal plane, for example, but perhaps in opposing directions. The total work done on an object equals the change in its kinetic energy. What is this? This is what we call the work energy theorem. You need to know this. So according to the work energy theorem, mathematically, the total work done on an object should be equal to the change in its kinetic energy, delta EK. And when we talk net work, you would see here now, it's as if we're referring to work as something that is a vector quantity. Yet we know that work is not a vector quantity, it's a scalar quantity. Now, why net here? Because friction also do work, okay, on objects. And we have friction, we have applied force. Okay, these two should always be noticed. I'm not saying this is that. I'm not saying that, but every time know that friction is acting and applied force is acting. Depending on how big your applied force is, we would either see some work done or no work being done. So friction also does work on objects. Okay, let's look at this example here. A cyclist of mass 65 kilograms cycles at 20 meters per second. He then applies a braking force of 400 newtons, which brings the bicycle to a halt. In other words, to rest, to stop. Calculate the stopping distance of the cyclist. And in this case here, let's assume that there is no force of friction here. All right. Now, if we assume that there is no friction, we can say that the work done, total work done, should be equal to delta EK. Now, remember that this came to a halt. So you've got this situation. You've got half mv squared final minus half mv squared initial, there, like that. Okay. Now, what was the final here? Half times 65 kilograms times v squared final was 0 because it came to stop, minus half times 65 times v squared initial, the initial velocity is 12. So that is 12 there. So this whole thing works out to 0. So this will be equal to minus, and we shouldn't forget that this must be squared. Okay, so we work it out as 65, half of 65 times 12 in brackets, you square that one, okay, and the kinetic energy is that. Therefore, W net equals minus 4680 joules. Okay, now you ask yourself, why are we getting a negative answer for work here? The reason is that the work done on the cyclist and his bike or her bike, it's a force that acts in the opposite direction of motion. So it's a force that is stopping that cyclist. And therefore the work done on it is a negative work, because it's a work that brings the cyclist to a stop, to a halt. Okay. Now, another example is this one. I may not have enough time on it, but let me start from it when we come back there. Maybe let me just unpack a few things here. It says a car engine exerts a force of 400 newtons on a car of mass 1,200 kilograms. The total frictional force between the car tires and the road is 1,200 newtons. Okay, then calculate the net work on the car after traveling 450 meters. Now, one way of working this out, I said earlier on, you might have to find the resultant force. Look, this is the applied force by the engine. That is the frictional force. You can quickly find Fres, which is your resultant, as the F applied minus F friction. And that will be equal to 4,000 minus 1,200. And that gives you 2,800 newtons. And from this, you have your Fres. You can work out the work, the work done by the resultant force. Let's meet in the next section.